Hello and welcome. Today, we're taking a deep dive into one of the most powerful and elegant techniques in mineral exploration, geochemical stream sampling. Think of it as reading the Earth's circulatory system. A stream and its network of tributaries, known as a drainage basin, acts like a giant natural funnel. It collects water, sediment, and dissolved minerals from every square inch of its catchment area and channels them to a single point. By taking a sample of this stream sediment, we're essentially getting a composite geochemical snapshot of the entire upstream area, which could be many, many square kilometers. This incredible efficiency is why stream sampling is a cornerstone of regional exploration. A single, well-chosen sample can represent a vast area, allowing us to rapidly assess huge tracts of land and zero in on promising drainage basins that might host a mineral deposit. So, let's explore how we use this technique, from the broadest reconnaissance scale right down to pinpointing a specific target. We'll break it down into 3 distinct phases. Phase 1 is regional reconnaissance. At this initial stage, our goal isn't to find the deposit itself, but to identify large, anomalous drainage basins that have the potential to host one. We're looking at a huge scale, often hundreds or even thousands of square kilometers. Our sampling density is very low, maybe one sample every 1 to 5 square kilometers, typically taken from the main rivers or major secondary streams. The workhorse method here is stream silt sampling. We collect the fine-grained fraction, the silt and clay, from the active stream sediment. Why the fine stuff? Because these tiny particles provide the best overall chemical signature of the catchment. They contain particles that have been transported in suspension and elements that have been chemically adsorbed onto clay and iron manganese oxides, giving us a comprehensive picture. The technique is straightforward but requires care. We find a good spot in the active stream channel, not the bank, and collect some sediment. We then pass this material through a fine mesh sieve, usually an 80 mesh screen, which has openings smaller than 180 micrometers. We often wash the sediment through the sieve using stream water. The fine slurry that passes through is what we're after. We collect this, let it dry, and place it in a labeled sample bag to be sent off to a laboratory for highly sensitive chemical analysis. At the same time, we often use a secondary method, creating a heavy mineral concentrate, or HMC. We'll take a much larger bulk sample, maybe several kilograms of sediment, from the same site and pan it right there in the field. This gives us immediate visual clues. Do we see any colors, which is our term for visible flakes of gold? Are there other heavy indicator minerals, like the tin mineral cassiterite or the tungsten mineral scheelite? This gives us a separate, physical data set that complements the chemical data from the silt sample. At the end of this phase, we'll have maps showing the concentration of our target metal, say gold, and its important pathfinder elements like arsenic or copper, across the entire region. We can now clearly see which drainage basins are hot and deserve a closer look. This brings us to Phase 2, prospect follow-up. We've identified an anomalous basin, and now our goal is to pinpoint the source of that anomaly within the basin. The scale shrinks to tens of square kilometers, and our sampling density increases dramatically. The strategy here is to walk the anomaly upstream. We start at our original discovery point and take new samples at every single tributary junction as we move up the drainage. While we continue to take silt samples, panning for a heavy mineral concentrate now becomes our dominant, real-time decision-making tool. Why does panning become so important here? Because it provides an immediate yes or no answer right in the field. Imagine we're at a fork in the stream. We pan a sample from the left tributary. Does it have gold? If yes, then we know the source is somewhere up that tributary, and that's the path we follow. If no, then the source must be further up the main channel, so we can bypass this tributary and continue upstream. We repeat this process, panning at each junction, systematically narrowing down the source location. When we finally take a sample just upstream of a junction and find no gold while the sample from the junction itself was positive, we know the point of entry for the mineralization is located in that specific stretch of stream between our last 2 sample sites. Alongside our panning, we continue to take silt samples. This allows us to map the chemical plume in high resolution and provides lab data to confirm the visual findings from our panning. By the end of Phase 2, we've achieved something remarkable. We have narrowed our search area from an entire drainage basin of many square kilometers down to a specific 100 to 500-meter-long section of a small stream. Now we enter Phase 3, detailed site investigation. Our focus shifts from the stream channel itself to the adjacent land, where we'll search for the in situ, or in place, source of the minerals. The scale is now very local, just a few hectares, and our sampling density is extremely high. Our first step is to transition from the stream to the land. We start by closely examining the banks of the anomalous stream section. We'll take samples of the bank material and look for float, which are angular, and transported pieces of mineralized rock found in the stream bed. An angular rock hasn't traveled far, which is a great clue. Next, we lines typically establish a grid on the slopes directly above the anomalous stream section and begin systematic soil sampling. This is the most common and effective follow-up to a successful stream survey. The soil anomalies will help us trace the dispersion of metals away from the source bedrock. Based on the patterns we see in the soil data, we might then dig trenches or pits. This allows us to expose the bedrock and the overlying weathered material, enabling direct geological mapping and channel sampling of the source structure itself. At the end of Phase 3, we have successfully transitioned from a regional stream anomaly to a defined soil anomaly on a hillside, and finally to a drill-ready target. Now, let's get into the nitty-gritty of the field methodology, because as a geologist, I can tell you that how and where you sample is everything. This is where experience and geological judgment are absolutely critical. First is the art of site selection. A poorly chosen site will give you a meaningless or misleading result. For stream silts, our chemical sample, you want to sample the active sediment where fine material naturally settles. This is often on the downstream side of gravel bars or in quiet pools. Critically, you must avoid sampling the bank material, as it's locally derived and not representative of the whole upstream catchment. For our heavy mineral concentrate, the physical sample we get from panning, you have to think like a gold particle. Gold is incredibly dense, so it drops out of the water current wherever the water's energy decreases. You have to find and sample these natural traps. Look for spots upstream of natural rock bars, in crevices and potholes in the bedrock, on the inside bends of meanders, and at the point where a steep, fast tributary joins a flatter, slower main stream. These are your high-probability locations. Next is the collection technique itself. For sieving, you'll use a stainless steel sieve. You place your sediment in the sieve and agitate it in the stream, washing the fine particles through into a pan or a special sample bag. Panning requires a bit of practice. You use a plastic pan, often green, to make gold flakes stand out. You fill the pot about 3/4 full of sediment from one of your trap sites. Submerge it and mix the material thoroughly with your hands to break up any clay and allow the heavy gold to sink to the bottom. Then, you begin a gentle swirling and shaking motion, letting the lighter sand and gravel wash over the lip of the pan. You continue this until you have only a small amount of heavy mineral concentrate left. With a final, gentle swirl of water, you can separate this concentrate into a tail of minerals sorted by density. If gold is present, you'll see it as tiny, bright spikes at the very top of this tail. Finally, and this is non-negotiable, you must have meticulous data recording. A sample bag with just a number on it is useless. A sample with good notes is priceless data. For every single site, you must record the sample number and GPS location. You also need to note the sample type, the stream conditions like width and flow rate, the character of the sediment and any nearby rock outcrops, and for your pen samples, detailed notes on the gold colors. How many did you see? Are they fine flakes or coarse grains? This information about the size and shape of the gold tells you about how far it has likely traveled from its source. This methodical progression, from regional anomaly to a specific drill target, shows why geochemical stream sampling is such a foundational tool. It perfectly blends sharp field observation with precise geochemistry to unlock the secrets hidden within a landscape. Thanks for watching. If you found this helpful, please like, share, and subscribe for more deep dives into the world of mineral exploration. See you next time.